Great, thanks for that introduction. Hopefully you can see a slide nice and clearly. So the background of having spent almost a decade in oil and gas is a really important part of this, because for anyone that has spent any time doing oil and gas exploration, the starting point was normally the cardboard boxes on the rack with the old data in before you could convince anyone to spend any more money on new data. So that idea of using the legacy data, what's already there, how much value do we assign to it? Can we make informed decisions using that legacy data, is a really important step before going all in with saying, well, we need to spend some more money, quite significant money, on acquiring new data. And in my whistle-stop tour today, you'll see effectively some of the summaries of two research projects. The first is all about using legacy data, compiling legacy data, and really trying to eke out the most you can from those archives. And then the second project, which is the picture on the screen on the right-hand side, is about a new seismic acquisition that we've done over this summer, actually, for geothermal purposes. So just to absolutely spell it out, because I spell it out to everyone, is that I think geothermal it's got a great potential to help us decarbonize heating in many of our urban areas, but we mustn't forget the huge challenge that the amount of energy in one barrel of oil, as you see on the left, several more joules than one barrel of hot water. That doesn't mean that barrel of hot water hasn't got a huge amount of value in our heating systems, whether that's, you've got to look to Germany, there's about 140 operating district heating schemes that use geothermal. It obviously works. The challenge is we have to massively drive down the cost difference in finding and developing that resource. There's lots of talk that the oil and gas industry can transition and be part of that movement that helps enable geothermal, particularly deep geothermal. But if you look at the costs and the amount of money that oil and gas companies spend on their exploration programs, we've got to drive that down by several orders of magnitude to make any of that technology, those acquisition methods, even remotely economic for geothermal projects. So we need to drive that down, whether that's geophysical acquisition, driving down the cost of geophysical acquisition, whether it's drilling, driving down the cost of drilling by perhaps getting away from bespoke designs, well designs, and having effectively copy and paste designs that work across an entire city or urban area. We've got to somehow drive down the cost, because when there's you can see it on the left, you've got that many billions of joules in one barrel of oil. You can spend quite a lot of money finding that, but you just can't for the hot water. About 3 years ago, I thought, we've got a rich treasure trove of data in the UK. There's a lot of data, whether it's legacy oil and gas data, legacy coal mining data. And the maps that you can see on the screen here are from 4 of the England's population centres with the highest heat demand. So the red colouring on each of these maps, let me just get my pointer. The red colouring on each of these maps is essentially the heat demand per area. So a darker red indicates higher heat demand, and a lighter colour, lower heat demand. And the little red outline is essentially grouping together urban areas, clusters where the total demand is typically over 10,000 megawatt hours per square kilometre. So really high clusters of heat demand. The rest of the overlays are our subsurface data. So the black dots are wells that are deeper than 500 meters within those areas. And the grey lines are existing seismic data. You'll notice a bit of a problem here, is that basically the seismic data is all around the outside of the urban areas. Perhaps not surprising, quite tricky to go and acquire seismic data in the middle of Birmingham, probably. Also, probably never really thought about looking for an oil and gas field beneath the center of Birmingham. There are a handful of deep wells, but we're talking 5, 6. And the same is true when you look around all these population centres, whether you look in London, Manchester and Liverpool, back in about late 70s, early 80s, Shell and others acquired some 2D seismic, which kind of ekes its way in there. So there's a little bit of legacy data. So there's a little bit more. But on the whole, you go around most of the population centres, there are areas of high heat demand, and actually our data is fairly limited. So that kind of leaves us with two choices, right? That means we dive in and go and acquire new data, quite costly, or we see what we can do with some of this legacy data to start with. So what you're going to see next is some examples of how we use some of the borehole data and revisited the legacy well data rather than the legacy seismic. The legacy seismic data is this huge challenge, which we also started to look at. For instance, we looked at, could you reprocess that legacy data? And it was really a mix. We found that sometimes you could find the nav file for the seismic line, and you could find the raw trace records. Therefore, you could look at reprocessing it, but sometimes you couldn't find the nav file. So all you had is the trace file, and reprocessing. Lots of these lines have lots of kinks in them. If you don't have the nav file and you've got lots of kinks in your 2D line, that reprocessing becomes quite challenging. It's also worth thinking that when I started on this, I came from a background where I was used to data being basically confidential, commercial, hidden away. If we want to enable geothermal, we need to think about the difference between available data and accessible data. So there is a lot of available data in the UK. There's lots of as we'll see, lots of borehole records in the UK which are not confidential, and you can access them, and they might be, but typically they are scanned images of reports, scanned images of logs. You can't batch download them. You have to download them one at a time. So is that data might be available, but it might not be accessible. And there's some really interesting definitions of accessible out there. And one of them that is frequently occurring in the computer science world is that for data to be accessible, it shouldn't require a human to go and hunt it out. It should be identifiable by a machine, i.e. using search terms and queries, and that should be enough to identify the data that you want. And so actually with working with Alex, who was a postdoc here for a year and a half, we actually did a piece of work where we basically said, well, where does all the data sit? Who's the custodian? How much of it is available? How much is it accessible? There's a huge amount of data in the UK's databases for the subsurface. But defining how much of this is accessible versus how much of this is only available is a really big challenge. Just because there are 1.3 million onshore boreholes records does not mean 1.3 million borehole records are accessible to use in your model build. So what do we do with legacy data? What does it look like? We had a project funded by one of the local enterprise partnerships, the Northeast Local Enterprise Partnership. Local enterprise partnerships are set there to kind of invigorate regions, to provide opportunities for business and economic growth, and also to support, for example, the challenges around people's mobility and commutes, to support the cost of living, energy. They're there to really support that region. We got funding to look at the deep geothermal potential across the Northeast area, which was essentially kind of North Tyneside, South Tyneside, and some of the surrounding areas. So we started looking at this legacy data. Here's a seismic line. This is what we're working with when we say legacy 2D seismic lines. Legacy well reports in the northeast of England. Most of it looked like this, scanned images, which had then been turned into a PDF. And sometimes you didn't even have the values themselves. Sometimes all you could find was a graph that had been created from the original values. And this is challenging. This is not machine identifiable on its own. This needs user input to do something with on the whole. So how do we take this? How do we do something useful? Well, we embarked on a mass digitization. We focused on our region because that's the area we had funding for. And Alex diligently set about building a structured database with complete metadata records for all of these individual borehole temperature and conductivity records we could find. Now, the BGS has done a great job back in kind of the 70s and 80s to compile lots of this into things like the British Geothermal Catalogue, but they remain as PDFs. Optical character recognition doesn't work that effectively on those PDF documents, so you can't just copy and paste those tables of data out. So we've gone down two routes. We've done some very laborious manual digitization, almost like a kind of QC step. And recently we've worked with a contractor to basically effectively throw the latest machine learning tools at it to identify the text. And so what we have now put together for the northeast of England and actually the Scottish borders as well. So there's quite a lot of data from kind of Edinburgh and south. We have digitized records for 250 boreholes. We have the complete suite of metadata. You can't see all these details, but this basically includes the drill date, the measurement date of the log, so they're not always the same. The measured depth of the well versus the log depth of the well, basically all that information that if you're a geologist working in a, in a small exploration geothermal company, all that information that you need to put in to be sure about what it is you're modeling in the first place. We've built it in a way that's a structured database as well. So we've used just CSV files because CSV files are basically readable by nearly every program that geoscientists use. So whether you're work in a large organization and use a commercial package, or whether you work in a research institute or in a university and you're more of a Python person, CSV files are flexible that nearly every single software package that geoscientists use can kind of ingest those. We've structured it so to make it manageable as well. So we have a master data table that has all these metadata records. We have a unique object identifier that links that master data table to individual temperature profiles logged in a well, individual conductivity measurements made in a well, and a set of formation tops from each of those wells. That object identifier is the same as the unique single onshore borehole index reference that the BGS use. So if you want to to make sure that actually you're not using a separate identifier, you're always using something consistent. And we've kind of grouped these by region. So we've done the Northeast and Scottish borders. And, as we get time and if we can find a little bit more money, we will move around and kind of carry on that process. So what does it look like? So geographically, these maps and plots from Alex. So these are the boreholes that we've got digitized so far. The different colors on the map indicate different data types available. What we also did is, where at all possible, there was a lot of circular referencing in all of the existing catalogs. So for instance, one geothermal compilation said, I got it from this reference, and that turned out just to be another compilation, and someone else had then referenced. So we found that there was lots of circular referencing. People were just referencing compilations for where they got their data. Where possible, we went back to the original reference. So you can go back to kind of 1870s for some of these, and you can find the measurement uncertainties as well, which is really important actually, because the further you go back in time, the more often those measurements are more uncertain. So it's actually really useful. And so actually, when we have a temperature log at a well, we've tried to, where possible, assign an uncertainty to that temperature measurement if it was stated. And the same for thermal conductivity measurements are made in the lab. We've tried to assign an uncertainty to those measurements. Why do we go to all that effort? Well, most of the modeling that we do in the subsurface has moved on a long way from single deterministic modeling. We've come a long way from only having the compute power to run single scenarios. And so we can include measurement uncertainty and all sorts of other uncertainties in our models, in probabilistic modeling. And so part of that is what this led Alex to kind of build, is how do we populate models in a systematic way? How do we include the uncertainties in those models? And how do we do it effectively, reliably, and repeatably? So this little workflow at the top shows how we could, different ways we could come up with assigning conductivities with depth in any of our models. It might seem somewhat tedious to go through that whole process of describing how you assign conductivity with depth. But actually, if you go in many modeling packages right now, it's kind of the user decides, right? So I could just assign the quaternary one value, and then I could assign the Jurassic deeper with a different value using a different method. We didn't want to do that. We wanted to say, right, we want to systematically assign conductivities, and ideally we'd always start with a measurement that was made, but perhaps didn't have a measurement, in which case we'd go to a report, and perhaps we'd have a lithology, and then we could assign it based on a measurement of conductivity in that lithology from elsewhere. But perhaps sometimes we didn't even have that data, and perhaps all we knew is just formation tops, and we didn't even have a description of lithology in the well because the data isn't accessible. And therefore we had to infer some lithologies from the stratigraphy and assign the conductivity from the lithology. It gave us a way to always trace back how we made a decision about parameterizing our models. Pretty much what that enabled Alex to do is to build probabilistic models for heat flow and temperature estimation in the subsurface. So rather than say, put one lot of numbers in and get one temperature or heat flow prediction out, actually you get a range of solutions out. And included in that are things like correcting for paleoclimate, which is sometimes done and sometimes not done. So if you went to the geothermal catalogs, there's a column and it says correction for paleoclimate, and some have got a yes, some have got nothing. And so it's really important, particularly when where we are in Newcastle, and as you head north into Scotland, that effect of paleoclimate and the past glaciation, if your temperature measurements were made in the top 500 meters of your well, they probably still see the effects of that past glaciation. So correcting for that is really important, as others like Paul Younger and Rob Westway have shown previously. So we kind of wrapped all this in. And so what do we get out? Well, actually, the plot on the right is the key to get out, is we get probability distributions for the heat flow at a location. And the one on the left, the red peaks, are without a paleoclimate correction. We don't take into account that the shallow measurements have been subdued by the past glaciation. And the one on the right, as others have shown previously, is with the paleoclimate correction. And basically you systematically underestimate heat flow if you don't take into account that. But because we compiled all the data in a systematic way, because we put together a workflow that systematically populated the parameters, we were able to do this at lots of locations quite quickly, because our data table had a standard format. So Alex's code, his Python code, was ingesting a standard format data table. There's no manual manipulation of the data table required. He had a workflow that said, if I have a measurement, use that. If I don't have a measurement, sample this. It had a way to pick up a value and assign values. And so quite, using nothing more than a standard laptop, we can now run probabilistic estimations of heat flow in individual boreholes. And lo and behold, actually, every single borehole we visited had an uplift in the estimated heat flow measurement based at that location, because these ones hadn't taken into account paleoclimate. And all of these measurements is pretty hard to see here, but these are kind of all within the top 300 to 500 meters, these measurements were made. So they've all got that paleoclimate impact. The current catalog hadn't corrected for them. We'd managed to compile it so they could be corrected. So this is kind of the value of compiling data in a standard digitized format, is it enables you to throw the latest tools at the problem. Without that painful digitization, you can't throw probabilistic modeling tools at these types of things. You can't run multiple models at once because all you've got is one borehole record. So it's kind of the first step to be able to do lots of the fancy stuff, the trendy stuff that we'd all probably like to spend more time doing. But to do that fancy, trendy stuff, we have to do that painstaking stuff at the start. It's worth saying the compilation of data, hopefully we're just finalizing that, and that will be available on a public repository. So it should be digitally available soon, and it's something we hope we'll be able to continue to build on. That's kind of the first half of the story. That's I've got some legacy data, how do I maximize the value? But what about if you haven't got any legacy data? We saw the maps, we saw, Birmingham didn't really have any seismic data, didn't have many deep wells. How are we going to characterize the subsurface? So this project is probably the most unlikely of funding streams that I ever thought I'd be involved in. This is a project on geothermal energy, effectively working with the RAF. So it's funded by the Defence Innovation Fund, and it's working with RAF Leeman, which is in North Yorkshire, so just off the A1M, if you're familiar with the area. And together, and the project led by Newcastle, by Oliver Heydrich, who's a life cycle analysis type of person. It's got these 6 different experiments. It's got carbon accounting. It's got a soil carbon capture project led by David Manning here at Newcastle. It's got decarbonizing power using solar, the latest PV materials with Professor Libby Gibson. It's got a sustainable ground transport with Professor Phil Blythe, and then it's got a piece on geothermal energy. And that's the piece we're doing. And this was all focused around the MOD, but more broadly, governments actually also need to decarbonize their estates and their infrastructure. They account for a huge proportion of government emissions. So I think the MOD contribute about 50% of all of the government's emissions. And that includes things like planes and aircraft carriers, but it also includes living accommodation. It also includes, those facilities that have to be heated. So actually, there's a lot of decarbonisation that needs to go on. And what we're doing with the RAF at RAF Leeman is we have a living lab, basically. These are experiments that are taking place in the real world. This isn't kind of, let's sit in our lab and do something and then see if we can apply it. This is, let's go to the base, let's look at its demand, let's look at its current energy needs. Let's look at how we could, in our case, how could we determine if geothermal energy is viable at an RAF base? If any of you have been to an MOD site, whether it's a RAF or other, one of the really interesting things is obviously there's a bunch of stuff that is part of the military, but then there's another part that just looks like you're in a small urban area. So in terms of acquiring geophysical data, it's a pretty good place to use as a living lab to see what would be the challenge of acquiring certain types of surveys in an urban area. And so what I was interested in is passive seismic imaging. We're probably, many of us, familiar with active source imaging, reflection imaging. So, we lay out our geophones and we get, in the past, maybe sticks of dynamite as our source in little drill holes. More recently, vibra-sized trucks, more recently, multiple vibra-sized trucks. That's great when you're working in, I don't know, North Africa, and you can have multiple vibra-sized trucks driving up and down in grid-like lines, and you can have cables stretched out everywhere, and you've got quite a lot of more flexibility around logistics. But in urban areas, You can go and acquire reflection surveys. They've done it in Europe recently, but it's quite challenging. It's also quite costly. If you look at the cost breakdown of a seismic survey, that source component of a seismic survey is quite a big cost. So what if we could use or make more use of that passive part of the experiment, the ambient noise? So there's two examples here. These are kind of, I guess, these are probably the examples that really kind of got me thinking about this. The first is from, for those of you that are familiar with CCS, it's from the Otway CO2 storage site in Australia. And here I only really need to explain the panel on the right, but the panel on the left is a traditional reflection survey, and the panel on the right is a traditional reflection survey, but the middle bar is an ambient noise imaging. So they effectively just used ambient noise to reconstruct a 250-meter long profile, and we'll touch on what methods we might use for that in that same location. Actually, you can see the fit's pretty good, right? And obviously that's we're just doing a qualitative fit with our eye, but when they went and investigated in more quantitative tools, they actually found out they could get quite a good fit using ambient noise imaging with a reflection image. So one of these had a bunch of sources and the other doesn't. Trick here is, though, they had a only 250-meter long line and they had a receiver every 10 meters. So it works, but that's quite a small area. The other end of the scale is some of the cool stuff that's been done in California out at Long Beach, where they had a high density 3D passive imaging experiment. And these are effectively the same types of images where they're looking to try and use ambient noise to characterize the interfaces. Here, they had 100-meter spacing. So they had a grid of basically 100 by 100, constrained obviously by infrastructure. They covered a much larger area. They covered about in excess of 25 kilometers squared, I think. So one of these was 250-meter lines, or one 250 line with a really close receiver spacing. And this was a bigger area, but with 100-meter receiver spacing. So I was then thinking, well, actually the middle ground here is we don't know yet whether really dense receiver spacing for a 3D style experiment, what value that has in the imaging. And there's lots of other kind of uncertainties. What record length, how long do we need to record that ambient noise for to reconstruct an image? Some of these experiments have shown that you can do it 10 days. Others have used 6, some have used 20. How much ambient noise recording do you need? And so effectively, that's our experiment. We want to look at, traditionally, this started off as looking at the response between 2 receivers. And we'll effectively understanding the Green's function, how a wave propagates between 2 receivers. And that gives you lots of correlations you can do. So for every, down in the bottom corner, you'll see a little equation. And this is the number of receiver events that you can correlate. So if you have 2 receivers, the number of correlations that you can do is just 2. Well, once if you have 6 receivers, you've actually got lots of different travel paths between the receiver pairs. You'll get the picture in a second. There's 18 possible correlations to help constrain the wave field in the subsurface with 6 receivers. Okay, so now start thinking about how computationally, how heavy this is getting. So now there's 52 receivers laid out here, and there's 1,300 possible combinations to help correlate and understand the wave field. This is our deployment. So on the right-hand side is the RAF base. This image is just a freely available satellite image. So you can pretty much make out where the boundary of the base would be, as denoted by the deployment of our receivers. So all of these little white dots is a receiver that was deployed. They were deployed in lines. They were pretty much deployed in lines because, one, we will also have a reflection process in which you'll hear about, but 2, it actually makes it a lot easier to deploy in lines when it comes to the practicalities. We worked with Stride on this. So the RAF funded and Stride were played a huge role in helping us deliver the deployment of this survey. We had one massive advantage of working within the confines of an RAF base like this, or a similar site, is that's one single landowner. One of the biggest challenges of deploying seismic surveys, and if you've ever been involved in one in the UK, you'll be aware of this, is that there are multiple landowners and you need the permission of each landowner to be able to go and do that activity in that setting. So having one single landowner massively made this a feasible project. As soon as you start adding in lots of individual small parcel landowners, it's not that you can't do it, but the kind of paperwork exponentially goes up. So we had a real benefit here. You can see a little zoom in on the left. So we have effectively deployed, we deployed receivers every 10 meters where we could, and the lines were spaced 100 meters apart. So if you remember back to the examples from Otway and from California, we're basically somewhere between the two. We've got much longer lines. In Otway, they only had a 250 meter line, where we've got lines that go in excess of 2 kilometers in our longest. So we've got long 2D lines with 10 meter spacing. But we also have this effectively 3D deployment as well, which makes it a bit like the California survey, except rather than being in excess of 20 square kilometers, we're about I think we're about a 5 kilometer square area in the end. So we're a smaller area. And we deployed in a variety of locations. So built-up areas, hence why you'll see in these built-up areas, the lines go a little bit wiggly. The practicalities of deploying in built-up areas are there's stuff in the way. So, for example, manhole covers, right? Can't put a seismometer on the ground on top of a manhole cover. Buildings get in the way. We also used, if you've ever seen the rail workers out there with their cable detectors to detect infrastructure that's buried, we also use cable detectors to make sure that we buried our receivers by about 15 centimeters. So we just made sure that we weren't burying near any buried infrastructure. So lots of ins and outs and quirks in the built up areas. Adjacent to the airfield, where there isn't much, you'll see almost perfectly straight lines, and we were able to deploy across the airfield areas. So when we analyze our data, some of the signals that we see will be quite varied, because I suspect when the planes are landing and we've got receivers located along the entire length of the runway, effectively, we should see the signal of a plane landing. Equally, we've already seen from a pilot data set that we had that modern seismometers, geophones pick up things like rotating noise from air conditioning as well, and they come out at a very distinct frequency on that data. So there's all sorts of different noise in a data set, and part of our project, well, because we had deployed across such a varied area, being able to characterize the different noise will be useful for both ambient noise imaging, but also for reflection processing as well, because we'll be able to identify noise and distinguish noise and signal. We also acquired source points. A traditional reflection survey enables us to have perhaps more confidence in then when we do the ambient noise imaging of saying, well, look, actually this is how good a job it's doing. So on the right-hand side, you can see all of our source points. It's kind of a pseudo 3D, right? I mean, in an ideal world, we'd have a lovely grid of shot points as well. But the realities of acquiring seismic data in built-up areas is that you've got to make the most of where you can get access to. So this is our shot points. And again, you can see the zoom in here. Some places we followed the roads where we're able to use the roads itself, get quite good coupling. But as you'll see, we also use grass areas as well. And expect, actually, given the ground conditions that most of us experienced during this summer, ground conditions were quite hard. So I don't think the source signal would have been impacted by any soft ground. What does deployment look like? This was quite a learning experience for me. Having spent probably, my PhD was in seismic interpretation. So I've been interpreting seismic data since about 2007, 6. I've never actually been in the field and acquired one. So this is what acquiring a seismic survey in academia takes. So I'll caveat that with this. This is a research project. If this was a commercial project, it could have looked very different. So we used the Stride node system. Here's racks of the nodes, the pre-deployment in the container. We used hand augers to effectively put them flush with the ground. There's two reasons to do that. One, we get good coupling. Two, there's a grass cutting regime near most airfields, and so we needed to ensure that the grass cutting could still carry on. So we were buried flush with the ground. You'll see one of our team here, Carrie. She's got a backpack on, which comes with the system, and we worked in teams of 3 or 4, depending on the area we're working in. One person typically had the backpack, one person had the auger, and one person had a can of spray paint, biodegradable spray paint, to mark the location, and actually the cable scanner. So we worked in teams of 3 or 4, and we used a total of 12 people, no more than 12 people on any single day. And in 12 days, 12 people deployed 3,500 receivers across the RAF base. Our team had no prior training. Okay, so we paid every single one of our student workers. We have a jobs on campus. It's kind of opportunities on that job website range from everything from cleaning halls of residence to being involved in research projects. And so students got paid for all of their day's work, and we gave them training. So that 12 days basically included one full day of training as well. So it's effectively 11 days. And none of them had any prior experience of geophysical surveying. So we were really happy. And actually, the piece that isn't the bullet point that probably should be is during the deployment, we had absolutely no HSSE incidents whatsoever, no near misses or incidents, which was a huge success, really, actually, considering the logistical challenge of deploying a seismic survey. We also had a series of shot points. Reese Geophysical did the shot point work for us. So we used a lightweight tractor mounted source vehicle. I think if my data is right, we've got about 1,300 shot point locations, which were required over 5 days, really efficient. And each shot point location has multiple weight drops as well. So we've kind of can improve our signal from looking at that as well. Again, like the deployment of the receivers, the acquisition of the shot points was made massively simpler because we did not use any public highways. So every road, if you've ever had a look, every highway in the UK has a designation. It's either public maintained at public expense and requires express permission of the council of that area, the highway group, to give you permission to carry out an activity. So even if that's just kind of, actually, even if we were walking along deploying receivers, we would have needed that. All of the roads within the RAF base didn't require that express permission. So we still went through a really vigorous pre-planning deployment process, but it just meant that we didn't need any external permissions to do those shot points. And this was really, it was a great outreach experience for all of us as well, because we would deploy in a survey and we would be walking, the tractor would be driving around and people would be going about their day jobs. And you know what? It didn't impact. It didn't make a difference. It didn't cause any undue delays to any other working activities. And likewise, when we were deploying the receivers, school was finishing and people were coming out of school and they were curious about what we were doing, but did it delay us? No, it didn't delay us. Were we an inconvenience? We weren't an inconvenience. We were a curiosity for sure. So what does that mean? Well, we've got 3,500 receivers. So for our passive seismic imaging, the total possible number of cross correlations to compute green functions is 6.125 million. That's probably not going to happen. That's because some of those receiver pairs won't be valuable. So we might find that for deep imaging, we're kind of interested in we're interested in deep geothermal. I always think deep has to be deep. It is 500 meters and greater. That's what's in legislation in the UK. So we're interested in 500 meters, 1,000, 2 kilometers. Some of these receiver spacings, the 10-meter spacings, might be too close to actually. There's not that much valuable information about that deeper section in those close pairs. So one of the first steps we're going to go through after we've looked at all the different signals we see is actually understanding, if we're interested in passive imaging at depth, which pairs are useful, which ones aren't. And Charlie, who's working on this project, this is very similar in many respects in terms of our workflow to the kind of piece you saw around legacy data, is we want to automate the bits we can. We don't want to have user input if we don't need user input. So as much as possible, this workflow that we're looking to build, which will effectively have, following the data QC, we'll do some of those more standard things, some bandpass filters, maybe some spectral whitening to basically clean that data up before the cross correlations. But this cross correlation phase, most of this can be automated. Most of this doesn't require that much manual input to do that cross correlation. Where it gets trickier is once you start wanting to look at the group and the phase velocities to then invert for VS. And that's the step that kind of is really interesting, because if you look at the work that came out of California and Long Beach, so inverting for VS, and actually they also have managed to invert for VP, that's where those velocity models start looking geological. And that for me is the point of this, that when you can get the geology out of this, that's when you kind of got that. So this is a case of watch this space, where the reflection imaging is kind of the easier part, I guess. The passive imaging, I suspect it will be mid-2023 by the time we get some initial idea of what we can see. And all of these projects have had a huge amount of support from varying people and companies and organizations. So we've got some funding from EPSRC, our local enterprise partnership, Stride, have provided a huge amount of support for our seismic surveying, the RAF through the Living Lab, and then we've got data. And yeah, this is just a short list of people who have made valuable contributions to every single bit that you've just seen. And that is a whistle-stop tour from old to new.